Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is the fourth video in Lecture 2.3, Incorporating Uncertainty into the EAD computation. In this section, we'll look at other metrics we can compute from the FDA computations, in addition to the expected annual damage. This is the fourth of our list of topics. So here we have FDA's computation approach that we saw earlier, with the three summary relationships on the left. And for one realization, we have one sampling of each of those curves from the uncertainty to be combined on the right. But instead of considering the stage damage curve in this case and going all the way to a damage frequency curve, we're going to look at only the first two, flow frequency and flow stage, that can combine into a stage probability curve. So from each realization, instead of going all the way to EAD, I'm pausing at a whole stage frequency curve. Right? So every realization will give me one stage frequency curve, and after all realizations, I'll have a large collection of stage frequency curves. All right, so here we're looking at a large collection of stage frequency curves. Right? We have stage on the vertical, exceedance probability on the horizontal, and recall that the zero is on the right, so an exceedance probability of 0 is on the right, and with increasing exceedance probability moving to the left. Let's consider for a moment the meaning of this collection of stage frequency curves. The collection of realizations is the sample, in this case the sample of an output. So this describes the knowledge uncertainty in the output based on randomly sampling the knowledge uncertainties in the two inputs, right? The knowledge uncertainty around the flow frequency curve and the flow stage curve. Right? So here we've captured the uncertainty in the stage frequency curve. Each realization is a possible reality of the stage frequency curve. And so for this collection of curve, each point also represents a possible outcome. So for a given stage, we have many different possible exceedance probabilities. For any exceedance probability, we have many possible stages, right? And the curves together reflect that uncertainty, as the sample would imply the probability distribution. If I was interested in one particular stage, and I wanted to know the annual exceedance probability of that stage, I would have a different result from each of these realizations, right? Every realization would show me a different annual exceedance probability for that stage. So for example, I have a stage of 44. These points are showing me that for each curve, if I come to that stage and down, I'm going to have a different annual exceedance probability, and it spans quite a range, right? So one computation that FDA will offer is an average of annual exceedance probability, okay? We're also going to show a different computation using these annual exceedance probabilities for assurance, and we'll get to that in a few slides. Okay. Another measure that we can compute from this collection of 1% stages is the conditional non-exceedance probability, or the CNP, also now known as assurance. So it used to be that to certify a levee as providing 1% protection, FEMA required the levee to be higher than the best estimate of the 1% stage plus 3 feet. When the Corps of Engineers started doing risk and uncertainty analysis, we cooperated to come up with a measure that could incorporate that analysis into the certification of the levee, right? And that metric was the conditional non-exceedance probability. So the conditional part of the name refers to the fact that it's based on one particular exceedance probability, or one vertical slice of this curve. And the non-exceedance probability refers to the likelihood that the stage of a certain exceedance probability is less than the levee. Right? So this is easier to look at than to say. Let's start with the 1%. You might remember that the 90% conditional non-exceedance probability is the stage that the levee must exceed. Right? So at 1%, I've cut the stage frequency curves to stop at 1% so we can see it a little bit more clearly. And the range of these curves trace out the uncertainty in what the 1% stage is. Right? So we've created this collection of stage frequency curves by combining the uncertainties in the flow frequency curves and the flow stage curves. So together they span the uncertainty in what the 1% stage might actually be. So this PDF describes the uncertainty in the 1% stage. And if we span 90% of that uncertainty, then we've described the stage with a 90% conditional non-exceedance probability for the 1% event. Right? So this stage has a 90% chance of being higher than the actual 1% stage. Now, FDA won't actually compute the stage that has a conditional 90% exceedance probability. What FDA will actually do is compute a histogram of the 1% stages, and then for a levy height that you offer, it will come over and look at how many of these 1% stages that levy will exceed. So this might say there's an 86% conditional non-exceedance probability for the top of the levy that was specified. So the conditional non-exceedance probability is one measure of assurance. We've also started talking about another measure of assurance that might be easier to understand. And that's the assurance that the annual exceedance probability of a given stage is less than 1%. Right? This image is showing both of those measures at the same time. So this is another set of stage frequency curves from a different FDA compute. In this case, we have a top of levy at 70 feet. So here's our 1% annual exceedance probability. And again, the red histogram is going to be our computation of the conditional non-exceedance probability at 1%. And if we cross the red histogram at 70, it's because we're interested in how many of these stage frequency curves have a 1% stage less than 70 feet. And that is 87% of those stage frequency curves, right? So given our uncertainty, we have an 87% chance that the 1% stage is less than 70 feet. Now, if we turn it sideways, we can look at the other measure of assurance, which is the likelihood that the AEP is less than 1%. This one over here. So remember a few slides ago, we said for a given stage, each of these stage frequency curves will offer a different annual exceedance probability, which is on the horizontal axis, right? Each of them crosses 70 feet at a different probability value. Now remember that the horizontal axis has 0 to the right, so smaller annual exceedance probabilities are to the right. So the blue histogram is a tally of the annual exceedance probability of 70 feet across all of our stage frequency curves. And if we look at 1% and tally up how many curves have an AEP that's less than 1%, it's again going to be 87%, right? And the reason there is because these two metrics are identical when we don't have any fragility curve involved. So let's look at the intersection of 70 feet and 1%. For any stage frequency curve that is below 70 for the 1% event, it's also going to be to the right of 1% for 70 feet, right? So any fragility curve that satisfies one metric is going to satisfy the other. So we're going to have the same percent of frequency curves, and so the same percent of our uncertainty to satisfy each metric. So this is true when we have no fragility curve. If we do have a fragility curve, which is the probability of levy failure at any given stage, then these two measures are no longer identical. And that's because with this computation, we take into account the fragility curve in two different ways for these two measures. For the conditional non-exceedance probability, this red histogram, I make use of the stage versus probability of failure curve by just reducing the bars of this histogram based on the probability of failure of the levy. So each of these bars of the histogram represents the portion of stage frequency curves that have a 1% stage in that range. And the fragility curve for that stage would tell us the probability that the levy actually fails anyway, and thus causes inundation, even though the stage is below the top of the levy. So I would reduce each of these histogram bars based on the probability of failure at that stage, because right now I'm counting a frequency curve as being below and thus satisfying if this 1% stage is less than 70 feet. But if I were to have the levy fail, even though the stage is less than 70 feet, then it doesn't satisfy anymore. So I reduce the histogram bar to not count it, and thus have a lower sum below 70 feet, and thus less than 87% as my conditional non-exceedance probability. Right, so that computation based on the fragility curve is done after all realizations are complete and after all of these stage frequency curves are finished and have been tabulated into the histogram. But to incorporate the fragility curve for the annual exceedance probability reflected by the blue histogram, I have to do a computation in every realization. So here's a depiction of how the fragility curve comes into the annual exceedance probability. I'll go through it quite quickly, but you can always pause and look at it a little bit more closely. So I have a simple levee fragility curve here on the left, which is the probability of failure of the levee for a given stage. I have the levee here. I have a series of stages. And in green, we have the stage frequency curve, which shows us the likelihood of exceedance for any given stage. In blue, I have a translation of this fragility curve, which is showing us the likelihood of the levee failing at each stage. So I divide up into a series of ranges, and in green, I'll have the likelihood of the stage being in each range. In blue, I'll have the likelihood of the levee failing if we're within each range, and the last column is the likelihood of both being within the range and the levee failing. So that is the likelihood of being at a particular stage and failing. If we sum those up across all of these stage ranges, we come up with the total exceedance probability, which is really a combination exceedance probability and failure probability. So for this example, the probability of the levee being exceeded was only 1%, but if we incorporate the probability of the levee failing, even at a level that doesn't exceed the top of the levee, that adds on another 4% annual exceedance probability for a total AEP of 5%. Now this computation will be done for every stage frequency curve in every realization, and so we can actually build a new histogram. Right? So here would be a histogram of the annual exceedance probability coming from each realization stage frequency curve without a fragility curve. And down here would be each of those annual exceedance probabilities being modified into a new histogram, with many of them being increased or moved to the left because of the probability of failure. So that's assurance of AEP being less than 1% compared to assurance as described by the conditional non-exceedance probability of the 1% event. All of those are metrics that we can compute with FDA based on the added uncertainty in all of those relationships. So if you have any questions about those metrics or any others that you might like to delve into, go to the discourse site and type in your question, and I'll try to be there real time and able to answer them. So that is the end of the fourth topic, and I'm just going to take a moment to run through the entire lecture, all 4 sections. Right? So we saw many things. First, we saw that EAD is the mean of the damage frequency relationship. We saw that EAD at some point on a stream or damage site is estimated from 3 summary relationships. We saw that estimates of uncertainty are now attached to each of those relationships, and that's going to result in uncertainty around the estimate of EAD. In the FDA software, Monte Carlo simulation is used to randomly sample those 3 relationships from their uncertainty with an estimate of EAD computed from each, and thus obtaining a distribution of uncertainty around EAD. Here's a point that was very important a few decades ago when we first started doing the risk and uncertainty analysis. And this is that the engineering and economic analysis that's done for this analysis where we consider uncertainty is really not that much different from the analysis that had been done before we considered the uncertainty. FDA's Monte Carlo samples entire curves, not just values. The number of Monte Carlo simulations required depends on the desired numerical accuracy, which is defined by the convergence criterion and how strict we need that convergence to be. Finally, we can compute other metrics such as annual exceedance probability, assurance that AEP is less than 1%, and this conditional non-exceedance probability of the 1% stage. Right, so that is the end of this lecture video. Thank you.